Good morning. Oh, we're all feeling a little low this morning, seems like. Understandable. Thank you for coming to our session. My name is Abhishek Sinha. I'm a Principal Product Manager at AWS. I manage a couple of services, Amazon EMR and Amazon Athena, two of them. Damon Cortesi is a big data architect. For today's session, it's a deep dive in what's new at EMR. So how many of you already use EMR? Oh, thank you. Thank you for your business. So when we thought about this session, we thought about a couple of things that we wanted to talk to you about. We've made a significant amount of releases in this year. We wanted to talk about that. And we've also noticed a lot of clear patterns in how customers use EMR. So what we will build those two patterns and give you advice on what we have found from our customers as the best practices of running those patterns, and what we have done in the entire year to accelerate or to make it easy to run those patterns on EMR. A lot of our customers, you would find that you are probably running one or the other of that pattern. So some of this might help you improve what you're already running. Some of this might help you add to what you're already running. So let's get in it. So as you know, that we release almost on a monthly basis. We released a new version of EMR almost on a monthly basis, where we have new open source packages in the distribution. We have about 16 different applications on EMR today. This year, we added Jupyter Hub, Livy, TensorFlow, and MXNet. We also added a significant amount of new features that were contributed back to open source. For example, the Spark Magic and Livy user impersonation with Jupyter Hub, that's what's contributed back to open source. Some of that actually came from you guys, where you told us that this was the problem when you were running, and we tried to solve it and contribute back to open source. How many of you are running HBase on S3, EMR's version of HBase on S3? So, some of you. So we also wrote a detailed guide on how to use and when to use HBase on S3. You can find this online as well. So and how to optimize those workloads. So here's an eye exam for you. If you can look at these applications, this is how we track about 16 to 19 different applications that run on top of EMR. And our commitment to you is that as long as there is an open source version that is stable, we will try and release it within the next release of EMR, at least within a 30-day time cycle. So at least till now, we have been able to do that, and hopefully we'll be able to continue on that commitment. How many of you know about the AWS Big Data Blog? Awesome. So for those of you who don't, there is a blog, like you have Jeff Barr's blog and the Compute blog and the Serverless blog. There is a blog on AWS called the AWS Big Data Blog. You can follow it by clicking subscribe to it. And a lot of what we do goes into this blog as feature releases. Also, a ton of articles written on this are by customers, by solution architects, or by big data architects that take EMR along with other components and help you build systems or help you build complete architectures. For example, we recently released a blog where auto-scaling policies were used to scale HDFS on a running cluster using elastic volumes on EBS. So as EBS released elastic volumes, we added that to auto-scaling, and it gets released as a blog. So do take a look at what happens on these blogs. There are several very interesting articles on this blog about things that you can do. So what do we see customers running? So we essentially see two architectural patterns of what customers run. We see customers running transient clusters. That means, and this is a fairly common pattern on top of the AWS cloud. I think the underpinning of this pattern is that if you have data in S3, running a 10-node cluster for 10 hours costs you exactly the same as running a 100-node cluster for 1 hour. So why wouldn't you scale up your cluster to 100 nodes, process your data, and then shut the cluster back down? We see this a lot with customers. The other pattern that we see is of persistent clusters, where you have a multi-tenanted persistent workload that never shuts down, but scales up and down using native auto-scaling policies that are on an EMR cluster. So predominantly, if you look at the workloads people are running on top of EMR, we can divide them into these two patterns. There's also the HBase pattern, which I think will address separately, but most of the use cases fall into these two patterns. So if you look at it from a workload perspective, the transient cluster is used largely for large-scale transformation. So, if you're doing Hive or Spark or Scala for ETL, that could be one of the use cases for transient cluster. It works very well. You have a scheduled job that runs every hour or a couple of hours. It spins up a cluster, finishes the job, spins down the cluster. The data is already in S3. So this transformation pattern can be used in multiple ways. It can be used to clean and compose a lot of data, convert the data from one format to another. It can also be used to load data into other systems or for ETL into other systems, and also for building extracts. So for example, we see a lot of you running ML jobs on top of EMR clusters that build extracts. The persistent use case is an interesting one because we see customers multi-tenanting ad hoc workloads. Now, the ad hoc workloads could be coming from a notebook. So Jupyter Notebook is a pretty common IDE that data scientists use. We often see multiple notebooks attached to a single cluster, which auto-scales based upon the amount of load that is pushed onto the cluster. We see a lot of experimentation on a persistent cluster. We'll have users log into the cluster, log into edge nodes, and run jobs for experimentation, for dev, and for testing of those clusters. We also see ad hoc usage of SQL, so Spark SQL or Presto, where somebody's logging into the cluster all through a Hive interface and then running queries on the cluster. Those are also use cases on this. If you're also doing transformation that is continuous, maybe in terms of streaming or maybe in terms of an hourly ETL, they're all fairly good reasons to run a persistent clusters. So one of the things that most of our customers ask us is, does everybody run transient cluster? Does everybody run persistent cluster? I think a good answer to this is depending upon the workload, people run a combination of transient and persistent clusters. Even in the world that we have seen with persistent clusters, we often see customers recycle their clusters for security updates every couple of days. And especially if you look at the workload and persistent clusters, there's often opportunity to recycle those as well. So it's not one versus the other. It's basically both of those patterns are perfectly viable for you as long as your workload fits that particular pattern. So let's talk about the first pattern, which is the transient cluster pattern. And if we try to condense all the best practices that we have heard from our customers who run this at scale, it would condense to something like this. Run as stateless as possible, automate everything, and try and template as much as possible. So what does that mean? It means that if you look at the transient clusters, we want to offload all the metadata or the state of the cluster. So one good example of this is connecting to the Hive metastore, or if you're using Hive, then taking the Hive database out of the cluster. Or if you're using Kerberos, then taking an external KDC, so on and so forth. There's also a use case around persisting your data in S3, so your state of where your source data is and your final data set is all in S3. There's also some best practices around how you submit jobs to build pipelines. Essentially, if you can automate the submission of your jobs so that clusters can run on a schedule, you basically have got this pattern down as a pipeline. And the last one is you can use Spot to reduce cost on these clusters, and a lot of our customers do. We'll talk a little bit about, and I'll show you some data about what we see from our end in terms of how the Spot usage has grown significantly. One pattern that we have seen is we see this great pattern of transient clusters that is used by a lot of customers. But customers often tell us, and especially data teams that are catering to the demands of multiple lines of businesses, they tell us that, OK, we get it. We know how to template these clusters. But how do I make sure that hundreds of lines of businesses that are now using EMR have the same template of running this cluster? How do I build a self-service platform where anybody can spin up a transient cluster and that adheres to the same kind of best practices that we design it for? And how will those manage costs? So we'll talk a little bit about that as well. So one of the basics of running stateless is you can take the metastore off the cluster. This is a fairly common use case, where you take the metastore off the cluster. It improves your startup time. It lowers your cost because you don't have to spin up the metadata server on every machine or every cluster, ingest all of that data. Fairly common pattern. We make it pretty easy to do this. You can use a configuration file on your EMR cluster that allows you to connect to a metastore. So early this year, or late last year, we released the AWS Glue Data Catalog, which is actually a drop-in replacement for the Hive metadata service or for the Hive metastore. So a lot of our customers have now migrated from using the Hive metastore to using the Glue Data Catalog. The benefit of the Glue Data Catalog is it is the shared metastore between services like EMR, Athena, Glue, and Redshift Spectrum. And what we note from a lot of our data teams is they don't use EMR only alone. They use EMR with a little bit of Athena, some Glue, a lot of Redshift, all of these together. So if you have a common metadata service like the Glue Data Catalog, which is a drop-in replacement from the Hive metastore, immensely helps that scenario. So connecting to the Glue catalog is also very simple. You basically point it to a factory. You use the configuration settings that are on the slide. Notice that there's also an account ID in there. That means you can also connect to a Glue data catalog that is sitting in a completely different account. And I'll talk about what is enabling this use case. We also released Finegrained Access on objects of the Glue data catalog. So for example, you can restrict access to a certain catalog. You can restrict access to a certain table. You can restrict access with a regular expression. You can also restrict access to a complete catalog. However, remember that this is only restricting access to the Glue metadata elements. It's not restricting access to data in S3 that still needs to be managed through S3. But a user needs both access to the Glue data catalog and access to S3 to execute maybe a query or run a particular job. So it's kind of adding another layer of fine-grained access control that you will see that you can use to control access. Also, you would have noticed the release of AWS Lake Formation this year. Lake Formation will further simplify this and further simplify making this really easy on the top of the Glue data catalog. So look out for those sessions on the AWS Lake Formation to learn more about that. A lot of teams told us that they have, especially in large organizations, they have a central data team and multiple lines of businesses. And central data teams want to expose a data catalog to other lines of businesses so that EMR clusters are running in their account. However, it is talking to the data sitting in the data team's account and the catalog sitting in their account. So it's a very good use case if you want to do cost attribution. So you can have your customers run in separate accounts and the data catalog in one account. So we enabled cross-account Glue data catalog access again this year. Pretty useful. We also build a bunch of scripts that can help you migrate the Hive metastore to the data catalog. There are a couple of ways of doing that. There's a bulk copy mode on the script. I would recommend that you do test the script before you use it in production. But this is maybe a direction that you could use to take data off your Hive metastore and then run it and then use the data catalog. So let's talk about this other pattern of using S3 to persist your data. We know the reads are fairly great on Amazon S3 because of the throughput that you get, and a lot of workloads running on EMR are throughput bound, except maybe the NoSQL ones. And but writes tend to be slower because of the way a bunch of committers are written. So committers are essentially pieces of code that write data to S3, and because S3 is not a POSIX compliant system, in the early days, the way you would write to S3 is you would write to a temporary file or a temporary location, and then you do a rename of all the files to move it into the right location. Tends to be really clunky and slow. So both in open source and EMRFS, which is EMR's own version of how it talks to S3, there are opportunities to improve the performance of this particular committer code. So we recently released a new committer called EMR S3 Optimized Committer that is available in 5.19. Significantly improves the performance of Spark when you write Parquet data onto S3. So instead of a two-step process, it basically writes it in one step using S3 multi-part uploads. Those of you familiar with multi-part uploads are essentially atomic. So it essentially uses the multi-part upload to commit data into S3 directly, avoiding the two-step process. And as you can see in the graphs that I'm putting up on the board, we see significant performance improvements between the file committer V1 and V2. There's also an open source equivalent of this that is available. It's your choice which one you want to use. This is our implementation. We also see that with this implementation, we can switch on speculative execution on S3 if you're using this implementation with Spark and Parquet. Speculative execution allows you to, has great performance or has benefits when you have a lot of straggler jobs. That means if your data has a lot of skew, there's going to be straggler jobs, and speculative execution improves the performance of straggler jobs. However, we have always kind of cautioned our customers in using speculative execution on top of S3. We generally turn it off because it can cause inconsistencies. But now with this new version of EMR FS committer, when you're using Spark and writing data to Parquet, you can definitely use speculative execution. It also shows a pretty good performance when you're using EMR-FS consistent view. EMR-FS consistent view is a part of EMR-FS that allows you to maintain consistency of objects between reads and writes. Also, with talking about S3, we also released integration with S3 Select. So S3 Select is a native S3 API that got released last year that allows you to push a predicate all the way down to an object. So for example, when Spark runs with S3, Spark basically pulls all the data from S3 into EC2 nodes and filters it in memory. With Spark integration of S3 Select, Spark does not pull all the data from S3. Instead, it pushes the predicate all the way down to S3. And then S3 returns only the resultant data back. So the idea is with the use of S3 Select, you get better performance. However, remember that S3 Select has a different cost profile than S3 has. So that's why we haven't defaulted all interactions to S3 Select, defaulted to all interactions to S3 Select on EMR clusters, but you have a choice of enabling that. It's available on CSV and JSON, and it's available in Spark, Hive, and Presto on top of EMR. So we ran some tests when we compared S3 Select to stock S3. So this was Presto running TPC, open source Presto running TPC DS100 queries on S3. And you would see that on some queries we see regression, but on most of the queries you see 40 to 60% performance improvement. Remember, it adds a different cost profile because S3 Select actually charges you for the amount of data that you get back also. There are two things to be cautious about when you're using S3 Select. One is if your queries don't filter any data, I mean, there's basically, you're not going to get a lot of benefit because you're still going to scan all the data and get charged for that data. However, also, if your data is in compressed format, S3 Select would have to decompress the data before it can filter. So that means sometimes you can get more data than what you had initially on S3 because it has to send the data back up into S3. So just be cautious of those two gotchas when you're using S3 Select. It's available today. You can switch it on. If you have queries which filter a large volume of data on CSV and JSON, I think you will get much better performance on S3 Select, as is evident in this chart. We also see several ways of submitting jobs to a cluster today, and especially a transient cluster. People use the EMR Step API, which submits jobs to the cluster. We also see AWS Step Functions. So how many of you know what step functions are? Fantastic. So there's a use case that we see where customers use AWS Step Functions to submit job to something like Livy, which has a REST API. Here's a good example of that. You can define your complete state machine in the step function. And each step of the step function can trigger a Lambda function to submit the job to Spark. So step functions essentially have three states. There is a task state. It can invoke a Lambda function. It can call the Livy server and submit a job. The next task actually retrieves the state of the previous job. And if the state of the previous job is a success, it can go into a choice state, whether it can take a path X or path Y. So something like this, you can build a complex tree or essentially a DAG, a relationship DAG, where you can take each of these elements in the step function and you can run them on an EMR cluster using this using the EMR Step API or the Livy server. Very interesting use cases. And we've seen a lot of customers migrate to this serverless way of submitting jobs to the cluster. Also, when you submit these jobs, you can go to this EMR Spark UI, and you can also see these jobs in the list of application history. When you click on any of these jobs, it also can take you to the exact logs associated with that particular job on the UI. We have seen customers do advanced orchestration where they trigger these jobs or they trigger these step functions based upon arrival of the data, based upon arrival of a metric or a CloudWatch alarm, or based on arrival of a manifest file. Those are all useful trigger functions. We have also seen orchestration based upon schedule. We have seen alerting based on failures, which step function provides. And we also seen parallel execution, where you have multiple streams of these DAGs parallelly submitting jobs to an EMR cluster. So very useful. So let's talk a little bit about Spot instances. We see a lot of our customers use Spot instances to reduce the cost of their EMR clusters, very much in the transient use case, but also in the persistent use case. And I think the fundamental reason is, imagine I have a cluster that's running for 14 hours, where each node on demand costs me $1. And let's say the cluster is running for 10 hours. So this cluster is costing me roughly about $140 for the entire operation. And now imagine I added 10 more nodes in Spot, and in my perfect world, let's assume that adding 10 more nodes, I have 20-node cluster now. Let's say adding 10 more nodes reduces my 14 hours of job time to 7 hours. Let's assume linear scalability. But so if you look at the cost of this cluster, assuming that all the Spot nodes that I got were a 50% discount, this is the cost of the cluster that you will get. You generally get a higher discount on Spot instances, about 80 to 90%, but I think it's safe to assume that it is at 50% discount from the on-demand price. So you would see that now by adding Spot, you've taken down 50% less runtime and 25% less cost. So what I tell my customers is the best use case or the best pattern for using Spot is you run the number of on-demand nodes that covers your worst case SLA for your business. If the worst case SLA for your business is 10 hours, where you want to finish a certain ETL, run those number of on-demand nodes, and then scale up using the Spot nodes. And every time you scale up, you will always finish your job faster and save cost, right? Because 10-node cluster running for 10 hours, it costs you the same as a 100-node cluster running for 1 hour. Now, on a day when you don't get the Spot instances, then you already are meeting your worst case SLA. This is the same pattern that we tell our customers to use in a persistent use case, where you have a persistent cluster that is running. Maybe that is a 10-node, 20-node, 50-node cluster, that you can get RIs for this, so you get the benefit of EC2 RI pricing on that. And then you scale up and down using the Spot instances. And when those instances get taken away, or let's say you don't find them in the Spot market, well, you were always provisioning for the worst case scenario. So using Spot every day is essentially gravy on top. I thought that will catch on a little bit more, but that's OK. So what do we hear from customers? We hear a couple of things from our customers when they complain about Spot. And especially we hear from customers who have been using Spot for a while that their problems kind of lie into these two distinct buckets. One is capacity related, and the second one is interruption related. The capacity-related problems are, we tried to run an M3 extra large or C4 extra large in US East 1, and we couldn't find any capacity. We waited for 30 minutes and 40 minutes, and we couldn't find any capacity. Or I was trying to launch in an AZ, I couldn't find any capacity. The other one is my Spot cluster was interrupted, or I had a cluster that was running the master node, and the master node was interrupted. Try not running the master node on Spot. That tends to kill the entire cluster a lot. If the Spot instance taken away. But there are also conditions where the Spot cluster was interrupted. Here is real data on the percentage of clusters that are interrupted by Spot across a complete month. And you will see that it is so low. It's less than 0.2 to 3%. And this is data that you can see on a month-by-month basis. You can see a spike and a low. But this is the percentage of all the Spot clusters that run on EMR, and there's lots and lots of them. How many of you use Spot with EMR today in this room? About half of you. When we looked into all of these interruptions and what percentage of these interruptions were, what were the reasons for these interruptions, we found 3 reasons. We found that you requested for a type of instance in a certain AZ and it wasn't available. We also found that the requested capacity in all AZs sometimes was not available. And we also found that termination of a single instance sometimes caused the entire cluster to fail. We had a bug in how we were provisioning our system, and especially on the core nodes, where if you take one node away on the core node, the entire cluster would fail. This wasn't the case with task nodes, but we saw our general guidance was don't run core nodes on Spot, run task nodes on Spot. If a Spot node goes away, that's fine, you will recover. But people also ran master nodes and core nodes, and we saw that even when the core node, if one instance was taken away, sometimes it will kill an entire cluster. So we have solved that problem. It was a very small percentage of the clusters. But if you look at the 3 issues that I listed down, the first 2 were the majority of the reasons people saw interruption or people who couldn't use Spot. And we figured that there was one basic reason. So Spot is a capacity. It's basically a market. And if you all invest in the market, what do? You don't invest everything in one stock. You try and diversify on the index, or you try and diversify across stock. So AWS has capacity that is available across a multitude of instances, but what we see in terms of interruptions is everybody is trying to get the same instance in the same AZ. So here's something called the Spot Bid Advisor. How many of you know about the Spot Bid Advisor? If you don't know about the Spot Bid Advisor, I would recommend that you Google it. It's on the Spot website. It's also it's a table. It's also an API that you could use. There is a nice little checkbox button there which talks about instances that EMR supports. But essentially, if you look at this table, you would see that the R4 4 extra large has 16 vCPUs and 32 gigs of RAM, sorry, 122 GB of RAM. And it is very similar to the R4 4 extra large, and they are almost at the same percentage discount, at about 73 and 74%. But one is at 5% interruption rate, and the other one is at 20% interruption rate. The 20% interruption rate is because everybody is trying to get the same instance at the same time in the same AZ, so the price has spiked up. But at the same time, there are other instances of similar capacity, similar discount, probably even higher discount that are available that look exactly the same, which we are not able to use. So it almost feels like there is an 8-lane highway, and for some reason, everybody is driving in the same lane, right? And then there is congestion. So most of our very experienced Spot users, what they do is they take instance groups. They try provisioning on a certain instance type. If they don't find it, they try provisioning on a different instance type. But they have instance flexibility. Essentially, what you're saying is, if I want to run my Spark job and I need something that has more than 16 gigs of RAM, 16 CPUs and 120 gigs of RAM, there are lots of choices within AWS. So we created something called the Instance Fleet API. What the Instance Fleet API does, it allows you to mix and match different instance types into one instance group. So the API works as this. You tell Instance Fleet, I want 160 cores, or I want maybe 1,000 cores on my cluster. I want certain amount of RAM, and I think that these particular instances are good for me. They can be from the same family. They can be from different family. They can be as big as multiple families. So for example, I want 1,000 cores. I'm fine with any 4 extra large machine, an R5, an R4, an R3, an M4, an M5. So I've given it 5 different options. So what the Instance Fleet does is every time if it sees a contention on the M5, it will pick the cheapest available instance in an AZ, and it will provision it for you. It will try and mix and match the instances so the cost of the cluster is the cheapest, and the chances of you getting interrupted are the lowest. You can still get interrupted, but the chances of you getting interrupted are the lowest. And this information is completely public. You remember the Spot Bid Advisor that I showed you, which shows you the percentage, the chances, the probability of you getting interrupted in a certain AZ when you use a certain instance type. It basically uses this information, but uses it as an API. So if you start one day and you programmatically decide that I want these 5 instances, they're all 5, you can have different EBS volumes attached to them, you can have different configuration per instance, and I'm going to use instance fleets to go and run that. And on a day when the price of, let's say, one single instance shoots up because everybody is trying to use those instances, you will be able to diversify across those instances. The other thing it does is, what if I do not have any spot capacity in a particular AZ on that particular day? It also allows you to fall back to on-demand after a certain timeout. So your general spot pattern is, give me 1,000 nodes amongst these choices, and if you can't, just switch me to on-demand. That is what the API does. So with the newer implementation of the instance fleets and also some of the newer processes, newer changes that we have made, you can see the cluster start time has also improved significantly. I think overall, our cluster startup time has improved by about 45% since the starting of the year. We continue to keep working on this, so you'll see faster and faster cluster startup time. Spot was a major reason why our startup times were a little slower, so we've changed our provisioning algorithm a certain bit. Now you can see the blue line was what we would see was the, all across our clusters, and the green line is what we see now. Pretty much smoothened out and also significantly lower. So instance fleets, you can mix and match instances between markets. You can say half of it I want on demand, half of it I want on spot, I want from multiple different instance types, so on and so forth. So the key to using Spot on AWS, or the key to using Spot on EMR, is to diversify across multiple instance types. Trust me, most of my customers who are actually doing this really well on Spot have orchestration that is built around EMR that does exactly this. We've also done a significant amount of work which has been contributed back to open source on Spark around decommissioning of Spot instances. So when Spot goes away, it gives you a 2-minute warning. And in that 2-minute warning, we try to safely decommission a job, or we try to remove that particular node so that Spark can fail a little bit more gracefully. It's not necessary that always that 2 minutes is enough for Spark to fail gracefully, but we try. This has been contributed back to OpenNode. What we do is we blacklist the node so that no other jobs can be taken, no other jobs are submitted to that particular node, and gracefully decommission the node using the 2-minute warning that Spot gives up. So these are all great best practices when you're running a transient cluster. What organizations tell us that this is great, but I don't want my data team to be continuously spinning up clusters. I don't want to ship code that everybody needs to use, to, especially lines of businesses. And especially when you have lines of businesses where there are data scientists and analysts who do not need to know the details about how we are spinning up clusters or what a multi-horn NIC really is. All they care about is logging into the clusters or using something like Jupyter to submit jobs to a particular cluster, and when their job is done, they basically want to shut down the cluster without. So how do we template this, and how do we build this in a way so that your entire organization can use the template? So this year we released integration with EMR, which is built, integration with AWS Service Catalog that allows you to build a self-service platform. How many of you know what Service Catalog is, AWS Service Catalog? Some of you. So the AWS Service Catalog is essentially a portfolio of products that you can expose to your organization that allows them to go pick a product and run that product. A product can be a CloudFormation template, or it can be a complete stack. So imagine I have a LAMP stack, and I can expose a LAMP stack to my entire organization. It also decouples the user of the stack, that means the consumer who is actually using the stack, from Service Catalog, which is actually provisioning it. That means I don't need to give all the users provisioning capabilities. One of the things that we often hear from customers is, I don't want data scientists to have provisioning capabilities of EC2 instances. I just want them to be able to provision EC2 instances, spin up the Jupyter notebooks, and then run jobs on top of the clusters, or just run Hive jobs. I don't want them to spin up hundreds and thousands of instances. You can template all of that in Service Catalog, and we'll show you a demo on this today as well. So you can standardize your deployments. You could say that in my organization, there are 3 standards of running EMR clusters. One is a 5-node cluster with these applications, these EBS volumes, this configuration, so on and so forth. You can enforce consistency and compliance. That means you can enforce what tags need to be associated with it. You can enforce what costs need to be associated with it. You can limit access. You can also do tagging and security controls, all baked into one. So nobody in your entire lines of businesses or your consumers don't need to know the nitty-gritties of running EMR clusters. They can essentially just go to the service catalog, spin up a product, log into the cluster, and that's it. For the consumer, it's also really simple because they really don't need to come to you to spin up a cluster. They can essentially go to the service catalog, spin up the cluster. They don't need EC2 permissions. They know that they're working on a templated product that has been vetted by you. They can automate deployment, and it essentially becomes a one-stop shop. You can, where you can enable a lot of governance. So from an administrator point of view, how does it work? So you are the author. You author a template. This can be a CloudFormation template. You can add parameters to the template. So one common parameter is where is your job? Where is your source data? Where is your source file? Where do you want your output? These can all be parameterized. You create a product, you build the template, and you release the product. We'll also show you how you have versions of product. You can build different layers on the product, so on and so forth. From a consumer point of view, they go on to AWS Service Catalog. There's a portfolio of products. Inside you choose a product, and you instantiate it. Pretty simple. So what that does is it changes the complete interaction the central data team is having with lines of businesses or with your consumers, especially consumers who have different levels of skill sets across the organization. So for example, here was the situation before. When a data scientist would come to an IT team and says, give me a new cluster, you would provision a new cluster for them because they might not really know how to do that or they might not want to do that. And then you give them access to the cluster. They log into the cluster. You have complex roles to define those, and they get access to the cluster. Now you have to continuously monitor or build programs that monitor whether the cluster was running. Did I need to shut it down? Is somebody still running the cluster? With the service catalog, what changes is there is a one-time request where data science says, I want these libraries, this version of Spark, a cluster with this configuration, this templates, this security settings. You build it as a template. You expose it on the AWS Management Console using the service catalog. You can also integrate it with things like ServiceNow. And the data scientist now goes to the console. It basically has a list of products. They can use a product, and they can expose the product. So let us show you a demo of service catalog integration with EMR. For that, I invite Dim.
All right. Good morning, everybody.
Sorry.
No problem. Just want to say a quick thank you to everybody for coming out this morning. Real pleasure to have you here, and also thank you for being here this whole week for reInvent. I know it's possible that it may have been a little bit crazy, but even as an internal AWS employee, I continue to be astounded and blown away by the breadth and scale at which we continue to release new services. It is truly mind-blowing, but enough of that. Thank you. Let's go into the demo. So what I want to show you today is using Service Catalog, and I want to give you the point of view from both an administrator, from creating a new product in Service Catalog, and then as a user, what would I do to provision a new cluster myself. So we've got our Service Catalog here, and I've created a portfolio inside the Service Catalog, which will contain the different products that I want to use. I've also customized the Service Catalog a little bit with my beautiful EMR logo up in the left-hand corner. You could even change the colors if you want to. But if I go into the portfolio, you can see I've got a couple different products in there. I've got a data science EMR and a data analyst EMR. If we go into the products list as an admin as well, we can see these two products in here and the description of them. So the data analyst one, we're going to create a cluster with Hive, Spark, and Hive for interactive queries. On the data science side, maybe we want to have some TensorFlow on there, some MXNet, whatever else you want for your ML, AI, advanced learning capabilities. It's pretty easy to create a new product. As Abhishek mentioned, you can use a CloudFormation template. So you have to go ahead and build that ahead of time. So what I'd like to show is, imagine you're building a data lake. You signed up for the lake formation preview, but it's not out yet, so you still need to build your own data lake. And maybe you use Athena for a lot of your ad hoc queries, but you want to give Presto to your users to allow them to spin up their own Presto cluster. And you want that cluster to auto-scale throughout the day. So when people come in at 8 a.m. and they're hitting their refresh button on their dashboard, the cluster's already scaled up and ready for that level of queries. And then at 5 o'clock, it scales back down. So I've got a handy CloudFormation template that I just happened to create back here. We can have parameters in the CloudFormation template, for example, the name of the cluster and the maximum size that we want to allow this cluster to auto-scale up to. We've got a simple resource in here for the EMR cluster, and in here we specify all the things that we might want to hide from the user that they don't really need to know about, right? We can specify the VPC subnet ID in here, the EC2 key name, the instance, specific instance types. And then we've also got the auto-scaling group in here. And this just defines the policy that says, OK, based on some metrics on the Presto cluster, auto-scale up in the morning and back down in the evening. So pretty straightforward CloudFormation template there. Back in Service Catalog, we can upload that new product. We'll create this, the name for it here. Give it a nice little description, maybe a cheeky description. And then we can say who it's provided by. In the next section here, we can provide support details as well. So if somebody runs into issues running that cluster, they know who to get in touch with. And then we either upload that file from our local machine or we put it on an S3 bucket and just provide that as the link there. We can also have different revisions in here. So I'll just put initial revision for now. Then we review that, go ahead and click create. And that uploads the product into the service catalog. So in a second here, that should show up after a little refresh. And now we've got our auto-scaling Presto cluster. We still need to add this to the portfolio, though. So we go there, add that product to the portfolio, and we'll just add it to our reInvent demo. So you can have one product that adds into multiple portfolios as well, right? Maybe you have a sales portfolio and a marketing portfolio or a data team portfolio. You can mix and match all those different products. Great. So now as an administrator, I've got a few different products in there. And let's see what a user sees when they go into this. So they go into their products list and they see the same thing we just saw, right? And I can decide whether to scale or launch something up. If I try to launch that Presto cluster, you can go in there and hit next, and you can see the different parameters that I mentioned in the job are provided in here as well. But for the purpose of this, I actually want to launch this nice data analyst EMR. So maybe I'm a data analyst, and I've got a little Spark script to do some data conversion, right? Pretty straightforward Spark script. You can see it's just taking an input location and an output location and converting it to Parquet. Pretty common thing when you're doing data analysis or data engineering is to do that Parquet conversion, right? I'm going to take a look at the Amazon Toys reviews, or Amazon Product Reviews data set for toys. I've got a 9-month-old at home, and I'm a first-time dad, and I want to use some machine learning to try to figure out what to buy for the little guy. Still figuring out this dad thing. So this Spark converter script, pretty straightforward, just going to read that TSV file in and then write it back out to Parquet in the S3 output location that I provide. So I go in, I create my, my data analyst cluster. I can have different revisions here as well. All my revisions are more functionally based, but you could essentially specify different EMR versions in here or different configurations that you want your users to be able to choose. I'm just going to select the latest revision. And again, here's where we fill in our parameters. So we're going to name the cluster. I've given the option to allow my user to choose a CPU or a memory-intensive cluster. So this will, behind the scenes, kind of choose the right kind of nodes that we want to run on. Since I'm doing data conversion, I'll lean towards CPU. And again, we could scale the cluster to whatever point we wanted to. We could also auto-terminate the EMR cluster. So if I just want to run the script and shut the cluster back down as soon as that script is done, we could set that to true. And then I have different job types here. So I'm going to select Spark. And then I have a set of inputs there. So those 3 inputs, those are essentially what's going to get passed to a Spark submit command, right? So you got the PySpark script, you've got the toys data set, and then the output location as well. So we'll go back there, hit next. We could enforce tags, maybe for billing purposes or something like that. And then we'll review everything and go ahead and click launch. Now behind the scenes, this is taking that CloudFormation template, filling it out with the parameters that we provided as part of the service catalog, and spinning up that CloudFormation stack. You can see a link to it right there if you really wanted to go over and take a look at that. And again, as Abhishek mentioned, this is something where I, as a user, don't need to have the permissions to actually spin up the EMR cluster, right? So this behind the scenes could use a completely different role that user doesn't need anything to get into that. So that cluster is going to go in provision, and when it's done, I've got it over here in my list. And you can even provide output parameters as well. So that cluster spun up, and now I provide the user with a link to maybe the EMR Resource Manager or the Spark History Server. So let's go take a look at that cluster right now. Here's my awesome Spark cluster. And as we mentioned, it's got C5 nodes there. So we decided to run compute heavy, and that was provisioned automatically behind the scenes. If we look at the steps of that cluster, you can see the step got submitted to the cluster. This is the Spark submit script that we pushed up to that cluster. It ran the job. It took a couple minutes, and that's that. Now, one of the nice things about this as well is we can go back to Service Catalog and we say, OK, I ran my script, and now I want to run another script, so I'm going to update my provisioned product. We'll choose that latest revision there again, and we'll go and update the parameters. And let's say, now that I have that data, I want to run a Hive query over it to kind of calculate the top toys over the course of that data set, right? So we've got this really simple Hive script that, again, takes an input location, an output location, and I'm going to provide those parameters to the CloudFormation or to the Service Catalog template as well. We'll go ahead, we'll hit next, and update the Service Catalog product. And behind the scenes, again, this is submitting the CloudFormation template, and CloudFormation is smart enough to just do a diff between those two versions of the templates. It says, OK, cool, the only difference here is I've got a new step. So if I go back to my EMR cluster, and the demo gods are lovely, and they are, we can see that now we've got a pending step in that cluster, and this is my Hive script that I used to essentially do that analysis. If I look out on S3, I've got my Spark output that I converted there, my Amazon product reviews data set in lovely snappy Parquet format, and there's also some Hive output that's getting written out there right now. And that would be the Hive output. So that's a good way that I can also, I as a user didn't have to provision that EMR cluster, didn't have to log into it, just submitted a few things. If I wanted to spin up a completely different Hive cluster as well, maybe I chose a memory-heavy cluster, I can do that as well. And so as a user, it's really easy for me to go in here, select those things, and spin up those clusters without too much of a worry. If you want something really, really end-to-end, there's an awesome post, of course, on the AWS Big Data Blog about using code pipeline and Service Catalog to deploy end-to-end. A simple example that I have up here. No demo god for me today. There we go. Sample Spark pipeline. So this is some source code that's in a repository. When any commits come in, this triggers a code pipeline and essentially goes through, does the build, does a QA deploy, does a test of that, and this is all spinning up Service Catalog stuff and CloudFormation templates in the background. And then you've got a live test approval here in the code pipeline as well. You could even hit review. Looks good to me. And then this will go out, build a new stack using the Service Catalog again. The user doesn't need any access to EMR. And you can actually do that entire deploy essentially in a serverless fashion using code pipeline. Pretty awesome stuff. That's it for now. I think without further ado, I'll invite Abhishek back up to continue.
That was awesome. Thank you. So we talked a lot about the transient cluster workload. Let's talk a little bit about the persistent cluster workload. The most important one and the most often used use case for persistent cluster is we see with Jupyter notebooks or with any kind of notebooks where data scientists want to use a notebook for maybe ML, for data engineering purposes, and they want to connect it to a cluster. We see a constant cluster which is multi-tenanted by multiple notebooks, and that can scale up and down. What users have told us is that it's really hard to set up Jupyter Hub. It's really hard to set up Jupyter on top of notebooks, and there is a lot of muck around using Jupyter today and allowing all the data scientists within your organization to use a simple use Jupyter notebook on top of EMR. So very recently, we released something called EMR Notebooks, which is a fully managed notebook environment built on Jupyter, based on open source Jupyter. So we'll talk a little bit about that. We'll also show you another demo of the Jupyter Hub notebook. But the core fundamental around running a persistent workload is, again, scale up and scale down. EMR already provides you native auto-scaling policies. You can take you can take metrics that are coming from Yarn or coming from Spark that are aggregated across the cluster. You can take metrics that are coming from the cluster itself, the cluster hardware that are aggregated. You can trigger CloudWatch alerts, and using CloudWatch alerts, you can call the auto-scaling cluster. Don't forget, you can also use Spot when you're using auto-scaling cluster. It becomes a really good way to save costs on a long-running cluster, where you have the on-demand clusters running using a reserved instance, so that's about 60 to 70% discount, and the scale-up using Spot instances. So my sagely advice on that is scale up and down as much as you can. So it's about 3 weeks ago, we released a completely new part of EMR called EMR Notebooks. Essentially, we're building a notebook environment that is decoupled from the cluster. It's based upon open source Jupyter. You'll get the same Jupyter notebook. You have to attach a notebook to a cluster to use the notebook, or you can also provision a completely new cluster directly from the notebook. Currently, it's only available on the console, but we will also make it available via API. You can have multiple notebooks or multiple users attach those notebooks to a single cluster that can auto-scale. That's also possible. You can also attach a notebook from a cluster, let's say your dev cluster, and then attach, detach, and then reattach it to a prod cluster. You can save the notebooks to S3. We're also going to add integrations with common Git repositories. And you can also do tag-based permissions. That means you could restrict access to the notebook using tags, and you can also restrict access to which notebook connects to which cluster using tags. So we're very excited about this idea of notebook. The notebook is completely managed. You don't have to manage any instances on the notebook. But remember, to execute any code on the notebook, you will have to attach the notebook to a running cluster, or you can directly provision a cluster as well. One of the use cases that we see here is with the auto-scaling policy that we imagine customers will take a long-running cluster, have multiple notebooks associated with the cluster, where the cluster would scale up during the day when more jobs are being tested on the cluster, and scale down during the night when not a lot of jobs are being run on the cluster. A pretty good example of how auto-scaling works, I took this from one of our users on Twitter, found it really beautiful that on the left-hand side, you can see ganglia graphs of how the cluster is gradually scaling up as the load is increasing on the cluster, and then slowly scaling down when the load starts to decrease in the cluster. So EMR scales in at Yarn task completion, because scaling in is also as important as scale up. You can also scale up your EBS volumes or your storage. So if you're using HDFS, which is fine if you're using HDFS. If you're using HDFS, you can scale out the HDFS. Be careful when you're scaling down HDFS. HDFS does rebalance when it scales down, so that's important to kind of note. We've also done several contributions where we can, as I said, we can scale down Spark slowly or gracefully, and we have contributed this back to open source as well. One of the things that customers ask us often is, when I run a persistent cluster, what happens when a master node goes down? We are working on what we're calling multi-master support for EMR applications. That's coming very soon. Depending upon what application that you're using, there will be different kinds of actions that you can take when a master node goes down. So for example, you can see this in this chart. When Yarn goes down, if you're using Yarn, you will have an active standby with automated failover and recovery. But if you're using Livy, Livy won't automatically fail, but Livy can recover. Livy has options to recover. So when the master, we'll have 3 masters, so that's why we're calling it multi-master. And when Livy kind of fails on one, it basically can recover. You'll have to start up Livy on another node, another master node, but you'll be able to recover it. So that's one of the things that a lot of our customers have asked us when they're running long-running persistent clusters, to give them an ability to use HA on the master node. We've also seen customers ask us for reconfiguration, where you'll be able to online reconfigure your EMR cluster or change the configuration of your EMR cluster without shutting down and starting a completely new cluster. So that's also an API that is coming. You will be able to do a rolling restart of the data nodes to prevent data loss. And one more thing with this is if you try to run a configuration and the configuration fails, it automatically defaults to the previous configuration. So all of this is coming fairly soon, but let me show you another demo of EMR notebooks, and for that, I invite Damon. Right?
Yep. All right, I'm back. So yeah, we'll take a look at notebooks. If you're at all familiar with EMR, which I'm assuming a lot of you are, on the left-hand side, you'll notice this new little section there that's just subtly titled Notebooks. So if you go in there, you can create a notebook. And it's pretty straightforward. We'll just name it, Damon's Notebook, add a description. And then here we can either choose an existing cluster, or we can even create a cluster inside the notebook interface. If we do that, we just get some basic options to create an EMR cluster. It takes whatever the most recent release of EMR is and adds on the necessary applications in order to spin that cluster up. You can choose your instance type in there as well, so maybe you want that P316XL for your favorite GPU applications. And then you could just go ahead and hit start. You can also provide tags, again, maybe for billing purposes or whatnot. By default, each EMR notebook is tagged with the creator of that notebook. So let's switch back to a different account here. And what we're going to do, we're actually going to choose an existing cluster to attach this notebook to. So again, we could put all that stuff in there. And if we want to choose where the notebook eventually gets saved to on S3, we could do that as well. But for now, we'll just leave that in the default location. So we'll go ahead, we'll create that notebook. Behind the scenes, this is provisioning that new Jupyter notebook. And if that comes up in the next second here, when you get into that notebook, you can start writing your code in there. So when you get in there, and that first time you execute the notebook, what's going to happen is the notebook is actually going to connect to Apache Livy on the EMR cluster and start up a Spark application in the EMR cluster. So that first command you run on there might take a little bit of time while it goes back to the cluster, starts that up. But once it does, you're good to go. And right here, you can also get some information that comes back from that in terms of the Yarn application ID. Maybe you need to do some debugging or dive into the logs or something. And that cluster back there already opened up as well. So if we open that up, we get that clean slate cluster back there, or notebook. But now we're going to do a little bit of data science-y type stuff. So I mentioned I've got that toys data set, and I want to go back there and do the analysis on the toys data set to figure out what I should buy my 9-month-old. So when you execute commands in here, again, this is going back to Livy and communicating with the EMR cluster. And we can see that we immediately get back some output. We went and read in that toys data set and printed out the schema so we know what we're working with. We can do a simple count on that data as well. When this goes back to the EMR cluster, we also get some feedback in the notebook interface in terms of what's happening. So we know that we went back, we just had these 10 tasks that we ran, and they finished pretty quickly. And we have maybe about 5 million reviews that we need to do some analysis of. I'll do a little bit of data shuffling here. I want to take that data, repartition it so I can redistribute it across my cluster a little bit better. And then I want to do a quick calculation of the top toys so I can see what to buy. If we go back to that cluster that this is running on, we can also see that we've got master, core, and task nodes. So my master and core nodes I put on R5s, and then my task nodes I put on C5s with Spot. So as different notebooks attach to this cluster, those task nodes can scale up to about 10 nodes and scale back down to 0 nodes. So it kind of scales dynamically throughout the day. If I go back there, I've already got some data back, and it looks like Cards Against Humanity is definitely what I should buy my 9-month-old for Christmas. So maybe we need to filter this data out a little bit, right? Let's do some kids ratings. So we'll just do a simple where query there. We'll filter anything out that doesn't contain baby or infant. Let's scope this down a little bit, right? We'll go ahead, we'll run this again. And as we saw before, we get the Spark job progress. So if we look at that, again, we can see the different tasks as they're progressing through, essentially in real time. We repartition this to 200 different partitions, and you can see it'll fly through those pretty quickly as well as it goes through and computes across the cluster. And we've got our output, and this definitely seems a little bit better, a little bit more age appropriate for me. Ironically enough, as I was working on this demo, this VTech SitToStand learning walker, it's a little thing like the kid can learn to walk on. Just bought that for my 9-month-old about a month ago. So it looks like I'm kind of on the right track here. So if I wanted to, I could continue doing some of my ML analysis, maybe take this product ID and find other users that reviewed that product favorably, and then what else did they buy? So super quick demo of how notebooks work. Pretty nice interface, allows you to just jump in there and be able to use notebooks on EMR really quickly.
Thank you.
Of course.
Thank you. Both of those. The demo gods are pleased at you, Jake. So that concludes our presentation. What we're trying to do here was give you a sense of what we have released in the year and how kind of it blends into our story of what architectures do we see customers running. There's some new stuff around notebooks. There's some stuff that is coming around reconfiguration and HA. That we are open for questions if you have any. We have about 2 minutes. Yeah, question.
So, like, EMR is foundational for some other fully managed services, like Athena and Wood. Curious about, like, you talked about the time frame for incorporating new versions and new version of Spark. How long it takes to incorporate that into release EMR? How long does it usually take for improvements to EMR, like the S3 Optimized Committer, to get added onto the other fully managed services that rely on EMR?
It depends. I mean, it's not necessary that those fully managed services do depend on EMR. Like Athena doesn't show you what it really depends on. So, and there are also, I manage both Athena and EMR, and Athena has a choice of, in AWS, teams work independently, so they have a choice of how quickly they can take it and they can write it. They have different kinds of challenges about how quickly they can take a patch. So for example, just being on the Athena and the EMR team, with EMR, it's fairly easy to get a new version out, right? Because you're opting into the new version yourself, right? You explicitly say, I want to use 5.18 or 5.19. However, on Athena, there's a single version. So there is a lot of testing and regression and that analysis. I mean, regression goes on both ways, but in Athena, it's a lot more difficult to kind of push newer versions out, so they're a lot more careful about adding new versions to this. But mostly we assume that all the products, if we make an improvement in Spark or Presto or Hive, it'll percolate through all the particular products. Generally, I would say 30 days to a couple of 6 to 8 weeks is when we expect. Yeah. I think S3N defaults to the normal protocol, but you don't need to use, S3A is the open source version. So if you just say S3, that should be all fine. You don't need to specify. I think N goes to S3A only. I've been told that we need to vacate here at 10:15 because for the next session. So we'll be here outside taking your questions.